Assalamu alaikum. Welcome back to our next lecture. If you remember, we spoke about how to solve a soil problem. We said that we have to have 5 steps. First one is to collect qualitative information. That's why we studied engineering geology, right? Second one is how to collect quantitative information. This information we studied them in statics, strength of materials, and we will study them in soil mechanics, including these things. We will explain them later. Plus economy, because engineering solution is an economical solution. Plus past experience. And then we said big plus. You see how big it is? Big plus engineering judgment or sense. Okay? This was explained last lecture. Now, we'll make a very brief and short and quick review to geology. Okay? You remember in geology, you studied several aspects, including cosmology, al-geology al-kawniyya, cosmology, in which we studied about galaxies, universe, galaxies, solar system, then Earth, right? And then in Earth, we studied that, you remember, we have Earth crust, right? Earth crust, then mantle, then core, right? Now, Earth crust composed of rocks. So, why we have to go like this? Okay. So we have rocks. In studying Earth, we concentrated on rocks. And you remember that we had 3 types of rocks, right? Igneous, نارية, sedimentary, رسوبية, metamorphic, متحولة. We studied this, okay? Why we concentrated on studying rocks? Because at that time we said that rocks consist of minerals, remember? And I think that you got something about types of minerals and how minerals are composed. Minerals consist of crystals, okay? And at that time you studied crystal groups, crystal faces, crystal angles, and then crystal types, okay? Crystals composed of atoms connected to each other by what we call it atomic bonds or molecular bonds. Whatever this, we have ionic bond, you remember? You studied this at school also. Ionic bonds, covalent bonds, hydrogen bond, right? Van der Waal bond, remember? You remember this? Van der Waal bond. Maybe you heard of London's bond, Rawabit London. Okay. So this we studied in geology. By knowing this, we reach to speak about soils, because soil usually composed of fractured rocks. You remember that rocks, by weathering and other type of effects, they are fragmented to small pieces. We call it soil, okay? So soil, mainly it is fractured rocks, okay? Soil aggregate, which is soil by other meaning, is summation of soil particles. So what we call it soil, it's mainly big number of soil particles, okay? Now, when we deal with soil, first thing is to classify soil, okay? Classifying soil makes it as groups, okay? Classifying soils. There are several points of views how to classify soils. As I told you earlier, those who deal with agriculture, okay, agricultural engineers, they deal with soil, but they classify it according to their needs, okay? Different than what we do. Those who study geology, they classify soils also according to their needs. Those who study mineralogy, mining, engineering, etc., all aspects of sciences. For us, classifying soil may be based on origin. Based on origin. What is the origin of that soil? Based on origin, we have two types of soils. We have residual and transported. Transported, transported, it was formed here, then moved to other place. Residual, it was formed here and it is still here, okay? Residual موقعية, transported, منقولة, okay? I have to speak some Arabics. Residual and transported, okay? Residual soil, there are several types, like residual, like saprolite, lateralite. You don't have to remember this or even to know anything about it. Just you have to know that there are residual soils and transported, okay? But there are some examples of residual soils. Now, transported soils, there are several types, like aeolian, which means that transported by air, okay? Transported by air. Most important is dune and Lewis. Now, Lewis, I think you must be familiar with this name. We use it a lot because in our country we have Lewis soils in several places, okay? We call it Turbat al-Lewis, even in Arabic, Turbat al-Lewis. Dune or Lewis. You don't have to memorize all of these things, but just to know residual and transported, okay? Now, we have also alluvial. If this is transported by air, this is transported by water, mainly from rivers, from lakes, from floods, you see? Or we have colluvial, which is transported on slopes, like in Nablus, in our city. When it is raining, all the dust and soils comes from above the mountains to the wadi, to the valley, okay? So this was transported by having slopes in the area, okay? So we call it colluvial. Glacial. Glacials, which was transported by glaciers. Glaciers means snow, ice. We don't have it here. But sometimes in areas like Canada, like Russia, like, areas where we have snow, we have rivers of snow. Okay, so these glaciers move soils from place to place. Or we have marine, which is on the coast of the seas. Okay, but we don't care about origin. Okay, it's not our job. This is the job of the geologists. That's why you should study this in geology. Okay, based on origin. It's not important for us now. What is important for us is based on size. We mean particle size. Particle size. Based on size. Particle size. How big is the particle size? Particle size, we mean diameter. Okay? But it may be not regular like this. Okay? What is the diameter? We have the biggest dimension. Okay? We consider the biggest dimension. But based on particle size, this is what is important for us. Okay? Based on size, based on particle size. Now we have also here several point views. Okay? For example, we have the German code. Okay? The Germans have their own point view about how to differentiate between components of soils. Gravel, sand, silt, clay. We'll talk about this later. We have the British standards, which gives different point of view. We have now European code. Okay? We have Italian, we have Russian, we have American, etc. Everybody has his own way of classifying soils. This is an example of the American way of classifying soils. Okay? These are all in the United States. Okay? We have the MIT, USDA, AASHTO. You are familiar with AASHTO, right? Did you hear about AASHTO? You know what is AASHTO. Or Unified. Let us go for the first one. Okay? MIT. MIT. What is MIT? It's a brief of Massachusetts Institute of Technology. Massachusetts if you are familiar, is a state in the United States. Okay, a state in the east, on the Atlantic Ocean, is very famous. Its capital is Boston. Okay, very famous. From the American Revolution began in Boston. Okay, so it's north of New York, on the East Coast. It has in Boston Massachusetts Institute of Technology, one of the best in the world, usually number one in the United States. Okay, it's very famous, very important. So that's why they have their own point of view. Okay, they say, okay, any particle bigger than 2 millimeters, we will consider it gravel. Gravel. I'll talk to you what is gravel later. Okay, gravel in brief. In Arabic we call it rukam. Okay, rukam. Although it has several other names. In some areas in the Arab world, in Egypt, for example, they call it zalat. Okay, in the Gulf areas, they call it sulbuh. Okay, in our areas, we call it hasa. Okay, hasma, whatever. We will use the word rukam. Okay, gravel. These are particles greater than 2 millimeters. Okay, greater than 2 millimeters. But for sand, you know sand, ramel, any particle from between 2 and 0.06 millimeters is called sand. Any particle between 0.06 and 0.002 is called silt. Silt. We don't have a real Arabic name for silt. It may be ghirian, tami, you know, it's mud. Okay, it's like clay. It's difficult to differentiate between them. Okay, now what is less than 0.002 millimeters? It's clay, tin. Okay, the MIT said, okay, these are my standards. Okay, now we have USDA. What is USDA? United States Department of Agriculture. By the way, in the United States, they use the word department instead of the word ministry sometimes. Okay, so saying Department of Agriculture, it means Ministry of Agriculture. Okay, it's not like here when I say department, you go to think of part of a college, right? Like Department of Civil Engineering. It's right, but it is used in the United States also as a ministry. So United States Department of Agriculture, they say more than 2.05, you see? You see the difference? From 0.05 to 0.002, less than 0.002. So this is the only difference. But this is for agriculture. You see, Department of Agriculture. We don't need to deal with agriculture. Now, we have AASHTO. You are familiar with AASHTO, right? What is AASHTO? What it is related to?
Transportation.
Transportation, good. American Association for State Highways and Transportation Officials. So it's transportation. So if you deal with transportation, you as civil engineers, you will study at least 3 courses in transportation and pavement design. You will deal always with AASHTO, only with AASHTO. Okay? So it's transportation. So what do they have? You see, because they are dealing with base course, you remember, you may be familiar with these things, okay? And with roads. So they have gravel, it has to be between 2 and 76.2. Sand, 2 to 0.075. Silt, 0.075 to 0.002. Less than 0.002 is clay. You see? This is for transportation, AASHTO. By the way, we will concentrate on AASHTO later on. Okay, we will use this. Okay? Now, they have MIT, USDA, AASHTO, and several other systems. Once they said, why to be like Arabs? Let us unite. Let us unite. So they decided to unite themselves in one system. So they had a meeting and formed the unified system. Unified system. They said, okay, between 76.2 to 4.75, this is gravel. Okay? Between 4.75 to 0.075, this is sand. Okay? Because they classified soils to only two sections, coarse and fines. Coarse and fines. Okay? So, coarse, they are greater than 0.75. Coarse, greater than 0.75. You see? Coarse means sand and gravel. So, this is coarse. Greater than 0.075. Okay? It is composed of sand from 0.075 to 4.75 and gravel greater than 4.75. And fines, which is composed of clay and silt, but they did not differentiate. What they considered less than 0.075, these are fines, okay, which is silt and clay. Okay? They have unified, but after that they disagreed. Everybody took his classification system, insisted on it, and we ended with having at least these four classification systems and more. Which one we will consider and which one will be used in our studying? This one, okay? This one, which is almost the unified system. Greater than 4.75, gravel. 4.75 to 0.075, sand. 0.075 to 0.001, silt. Less than 0.001, clay. So this is finally we will use. This one we will use. Okay? So when we say gravel, immediately you will know. Gravel, more than 4.75. Sand, 4.75 to 0.075. Silt, 0.075 to 0.001. Less than 0.001, clay. Okay? So when we deal with the classification systems later on, we will deal with this system. Okay? This system. This is for building. Okay. Now, what is gravel? What is sand? What is silt? What is clay? Okay? Because we spoke about them. Okay. Soil consists of gravel, sand, silt, clay. Gravel, rukam. What is gravel? Pieces of fragmented rocks with occasional particles of quartz and feldspar. Quartz and feldspar. You must know what is quartz and feldspar or fluorspar from geology. Quartz, number 7 in Mohr scale. You remember Mohr scale for toughness, for stiffness, for hardness. Mohr scale. It's number 7. Okay. So it is gravel, mainly quartz and feldspar. It's pieces of rocks. So the characteristics and behavior of this gravel is the same characteristics and behavior of the rock that it was formed from. Okay? It has the same thing because it's fragmented or fractured rocks. Now sand. Sand, it's mainly particles of quartz and feldspar. That's why in our mind, quartz, when we say, okay, what do you know about quartz? You say sand, right? Most people know that sand, mostly quartz. That's why we have this relationship. Okay, so sand it's particles of quartz and feldspar. Now, what is silt? It's particles of quartz and feldspar, but microscopic, very small, microscopic particles of quartz and feldspar. As for clay, it's something different. Clay consists of clay minerals. We call it clay minerals. We have something called clay minerals. Clay minerals are a very huge family. Actually, they are families. Okay? Families. And the behavior of this clay is affected by what family it was formed from. Okay? What kind of family? Now, if we have so many hundreds of families, let us have three examples. One shows us the extreme left, one shows the extreme right, and one shows the extreme middle. Okay? Medium. I chose three families, okay? Three very important and well-known families of clay minerals, as an example, just to understand why clays are different in their behavior. Let us have the family kaolinite. This is a very important, famous, and maybe the hugest family of clay minerals. Kaolinite, or sometimes it's called smectite. Okay, kaolinite or smectite. Kaolinite, it's a family. Let us consider it this extreme left. Okay? Now, we have the extreme right, montmorillonite. Difficult, I know. Montmorillonite. And let us have something in between, in the middle. It's called the family of illite. So we have three families. Just to compare between them and know why this clay behave like this, why that one behave like different, okay? So we have three families: kaolinite, illite, montmorillonite. Kaolinite family has hundreds of members, okay? So we will have the most important member of it, Mr. Kaolin. Kaolin, type of clay, we call it kaolin, okay? Kaolin is the sole representative of kaolinite. Actually, it's the most important, the most famous of the family kaolinite. So kaolin is from the family kaolinite. Illite is from the most important or the most famous member of the illite family. Okay? How come? It happens even in our life, right? The person's name is the same name of his family. You know that. Okay, so illite. Bentonite is the most important member of the montmorillonite family. Okay? Now, what are the difference between them? Sorry. Of course, the difference comes from the beginning. The beginning is atomic structure, right? Atomic structures. Atoms are connected to each other by bonds. They form sheets and layers. Sheets and layers are repeated several times to compose molecule. Okay? And molecules together, several hundred of them maybe, or several tens of them, they compose the particle. You remember? It's like, let me explain it like this. We have a library, consists of hundreds of books. Every book has hundreds of pages. Every page has hundreds of letters written in it, right? So, particle consists of molecules, several. Okay? Molecule composed of sheets and layers, several sheets and layers. And every sheet or layer composed of atoms connected to each other. It may be hydrogen with oxygen, with the silicon, with the potassium, with the magnesium, whatever. Okay? Now, drawing how crystals are connected to each other is very difficult. Even if you studied drawing, engineering drawing, you studied, right? Engineering drawing 1. If you studied engineering drawing 100, number 100, okay, you'll not be able to draw the crystal structures. They are very difficult to draw. That's why we have a symbolic drawing for it. Symbolic drawing. Okay? So we draw them by symbols. Like, for example, the kaolinite and bentonite and montmorillonite mainly composed of gypsum and silica. You know silica? SiO2. It was very important. When you studied minerals, you know that the most famous group of the minerals is the silica, right? Silicates, group silicates, right? It's the most important because it's the most common. Almost every rock in the world has silica on it. Okay, it's the most important, silicate. Okay, and it is divided to silicate, pyroxenes, mica, and some others. Okay, So it's very important. It's almost in every mineral. It's almost in every rock. Okay? Silica. So what we have? We have, this is silica. And this is gyps. Okay? Gypsum. You know gypsum. Okay? So silica gypsum. This is sheet of silica, sheet of gypsum. They are connected to each other by hydrogen bond. This is very, very strong hydrogen bond. Okay? Again, silica, gyps connected to each other by hydrogen bonds, and so on. So on, several sheets and layers of silica gyps, silica gyps, silica gyps. Okay? So they are repeated several times. Silica gyps, silica gyps, silica gyps. Now, what is important for us when we have to classify minerals is what is the composition. Like here we have silica gyps, right? We may have potassium and silica. We may have aluminum. We may have ferrum, iron, etc. Right? So what are the components first? And another thing is this distance. You see this distance? The distance from the head to the head. The distance from the base to the base, you see? Because mostly this distance is fixed. We call it basal distance. Basal distance. Basal distance. The distance between from the head to the head, from head to head, or from base to base, right? It's fixed. It is fixed. Like, for example, in kaolinite, in kaolin, the basal distance is 7.2. What is this? What is this unit? What do you know about this unit?
Angstrom.
Angstrom, right. Angstrom. What is angstrom? Angstrom.
10
Angstrom. You know this small millimeter on your ruler? Small millimeter? Millimeter, 1 millimeter. Divided to 1 million part. Every part is an angstrom. You see? Angstrom is part of 1 million part of the millimeter. You see how small it is? The basal distance is 7.2 angstrom. So the distance from here to here is 7.2 part of 1 million part of a millimeter. You see how small it is? Then how when we go inside the silica, inside the gypsum? You see how small it is? Okay. Kaolinite, kaolin. Silica gyps, 7.2 angstrom. Okay. The basal distance. This gives us a kaolinite. On the other hand, we have bentonite. Okay. Bentonite, sandwich of gypsum, okay, gypsum, layer of gypsum, sandwich between two layers of silica, silica gyps, silica, silica gyps, silica, you see? And the basal distance, it's from 9.6 to complete separation, to infinity, to complete separation angstrom. So it's variable, it's not fixed. Like here we have it fixed, 7.2, right? But here we have it 9.6 to complete separation. To complete separation. Silica gyps, silica. Silica gyps, silica. Okay? We'll go back to this later. Let me say something. Based on that, you see, look. Kaolin, bentonite, you see? Particle size, kaolin, it's not big. It's very small. But comparing with bentonite, it's bigger than bentonite. You see? It's bigger, smaller. We are talking about very small particles. For clay, it's less than 0.001 millimeters. You know what is 0.001 millimeter? 1 micron, right? 1 micron. The millimeter, divide it to 1,000 pieces. Every piece is micron, right? Micron. 1,000 angstrom. So we are talking about very small. So you cannot say big. It's big compared with bentonite. So it's bigger, smaller, particle shape. Okay, we will not speak about it. Plasticity, activity, swelling, and compressibility. This is important. Swelling, you know what is swelling, okay? When any material, we put it in water, so it heaves. It heaves. So swelling. It becomes bigger, right? Swelling, intifakh. Compressibility, the opposite. Hubut. Okay? Activity, the process of swelling and compressibility and reactivity. Okay? So you see here, low, 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 high, 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 high. Why it is low here? Why it is high here? We go back to where we were. Okay? Why here we have swelling, compressibility, activity, plasticity low, comparing with bentonite? Why we have 7.2 angstrom fixed, why we have 9.6 to infinity, to complete separation? It means that water comes here, okay, from all directions, and then let soils go away from each other. Why we have this bentonite? This bentonite, by the way, we call it troublemaker soil. We don't like it. As engineers, we don't like to have bentonite. When we see bentonite, we run away from that project. Okay, we don't like it. Why? Because it's a troublemaker soil. It has very high swelling, very high compressibility, very high volume change. We don't like it. It's a troublemaker. Okay, so why it is a troublemaker, and why kaolinite doesn't have big volume change, doesn't have big swelling, doesn't have big compressibility, doesn't have big plasticity, doesn't have big reactivity or activity, while on the other side, bentonite. From here, we know the difference. Anybody has any suggestion? Why we have this difference? Okay, let us go to basic chemistry. Basic chemistry. When we have two elements, one has at the end a negative charge, the other one is a positive charge. So what kind of bond between them? Okay, when we have negative and positives, then we have bond, right? But when we have negative and negative, or positive and positive, then they go away. You know, tanafur wa tajadhub, okay? When we have similar charge, then things go away from each other, right? But when we have different charge, then there is a strong bond, right? Here, you see, we have gyps, we have silica. Silica negative, gyps positive. Then we have strong bond here, strong. When it is strong, it doesn't allow anything, including water, to go inside. Then it will not swell, it will not heave, it will not have a plasticity as big as bentonite, right? But here, what we have? We have silica and silica, negative and negative. So they are all already going away from each other without anything. That's why when water comes, it is easy to water to come between these two sheets and then divide the particles and let them go away. That's why we have to complete separation. That's why we call this soil, we call it in Arabic, عاشق للماء. It absorbs water. It absorbs water. Even when we don't have water. How come? Even we don't have water, but still this soil absorbs water and swell and heave. How come? From where it brings water? From humidity. From humidity. Even from the humidity of the air, it absorbs water and then heave. Okay? That's why it is a very problematic soil. Okay? Now we know why we have this. Low, 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 low. High, 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 high. Right? Because of this structure. You see? Here we have different charges, so we have very strong bond. Here we have similar charges, so they are getting away from each other and allowing water to go inside. You see? Now, if we go back to this table, about a light, we see what? Medium, 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 medium in all aspects, right? Medium in all aspects. Why we have it medium? Although it has silica, gyps, silica, silica, gyps, silica. And basal distance is 10. It should behave like bentonite, right? Right? It should behave like bentonite because it has the same thing, silica, gyps, silica, silica, gyps, silica. But it doesn't swell as much. It doesn't consolidate as much. It doesn't react as much. It's not active as much. It's not plastic as much. It's medium between bentonite and kaolinite. Why? Why it's medium? Unfortunately, I have to draw this before. So I'll give you a hint. Because it has here cations. Cations. Negative, negative, but I have a positive cations. Ions, positive ions. I have them here in between, mainly from potassium. Mainly from potassium. So it makes the bond here stronger than here, weaker than here. Okay, so these kind of cations, they exist in the soil. So they come in between the layers. Okay, joining hand from here and make silicates close to each other. Silicates from both sides. So that's why we have here medium. Okay, so why we sometimes have some kind of clay, swelling clay, why we don't have swelling clay, why we have compressible clay, why we don't have compressible clay. We go back to crystal structure. You know how important to study crystallography in geology? You didn't know that when you studied it, right? You did not think of it. But this is why we study such things. Okay. So these are 3 examples of clays. Kaolinite, illite, bentonite. And based on that, low, medium, high. Okay? And now if even we compared particle size of the particles, we know that kaolin is bigger than illite. Illite is bigger than bentonite. Okay? And if we compare particle shape, kaolin almost rounded. Okay? Rounded. This is also important. While illite is medium, angular, like this, almost rounded. While bentonite is flaky. Flakes. You know corn flakes? Flakes, sheets, layers, you see? Also, this shape is very important to give behavior later. You see? Because, for example, the destruction of rounded particle is not easy as the destruction of flakes, right? Right or wrong? None of them? What is easier, to destroy, to crush a rounded particle or a flaky particle? Okay. Thanks. Flaky. So that's why bentonite can be crushed easily. Once it's crushed, so it comes to smaller, still smaller particles, right? Smaller and smaller. And this is important because when we have charges on the surface, and the surface, the bentonite, comes to very small particles, so we have charges, more charges. The specific surface is more in rounded or in many small flaky particles. Specific surface. What is big? The specific surface of this circle or of these circles inside this circle. Specific surface, not surface. Specific surface. You know, the specific surface of the small particles are more bigger, more greater. Specific surface. Summation of all surfaces of all small particles. So that means we have here more charge than here, right? We have more charge, right? Okay, another thing. We have more charge and still the particle is very small. While we have smaller charge, but the particle is big. So where is the bond will be greater? More effective. When we have huge charge and it has to pull, okay, very small, tiny particle. While we have some charges, but it has to pull very huge particle. Where's the effect will be more? In the first or second? In the first, of course. I have many charges, they have to pull the key. But I have small charges, they have to pull the disk, the table. Okay? So that's why we have charges here very effective, very strong. Charges here very effective, very strong. Okay? Now, so we go back to gravel, sand, silt, and clay, right? We have to classify soils to gravel, sand, silt, and clay. How we can classify them? We'll take a ruler and sit near the soil and take every particle measure. Okay, sand, gravel, silt, clay. Can we do that? Of course it's useless, right? We have several methods. One of them, actually, the most important of them is sieve analysis. You know sieve analysis? Okay. You seem sad to know it. Sieve analysis. Sieve analysis is a method that consists of several sieves put together like this, okay, and covered by a cover. This is a cover. The last of them is not a sieve. We call it pan, right? Sieve analysis. Our next lecture will begin with sieve analysis, okay? Thank you.